Good afternoon. So we carry on with our chapter 8. We've got 2 more sessions to finish this chapter. As you know, this is the longest chapter, so it's taken so long actually to complete this. So last week I did this example, which was on a turbine, and we looked at 2 cases where we had just a turbine, and and the second example was where we had a valve, a throttle, before the turbine. I'm going to do 2 more examples on this, and then I'm going to carry on with the rest of the lecture. So one important thing which I mentioned about the turbine was that, so we looked at different devices, including the turbine, compressor, a nozzle, etc. One of the important things which I mentioned was that you need to look for what is common before and after that device. So, for example, turbine is an isentropic device, which means entropy will be the same before and after, and you use that information to translate or in order to be able to find other parameters, such as entropy, for example, and that's exactly how you approach these problems. So I'm now moving on to the second example, which is quite short. This case is just looking at ammonia. And again, we just want to look at a very simple example where you would find out where you calculate entropy. So let's just make sure you know where to look for in your steam tables when it comes to ammonia. So in this case, we've got ammonia, and the initial temperature is 2 Celsius, so that's T1. The dryness fraction is 0.1, so your X is 0.1. It is then heated until it's dry saturated. The dry saturated means that X is now increased to 1. And whenever it's dry saturated, then you're dealing with things which have subscript G. So SG, HG, etc., VG. So we want to find out the change in entropy. We've done lots of similar examples in the past, but without looking into entropy. So you've done the same thing for enthalpy, for the specific volume, for example, and other things. This is now just focusing on entropy. So if you go to page 13 on your steam tables, in your tables, that's where the ammonia data is found. The first thing you do is you look at temperature 2 Celsius. And in fact, I'm just going to show you quickly because this one is simple. So if you go to page 13, that's your table. And then if you look at temperature 2 Celsius, that's here. And then you read off the values on this row. The things that you're interested in now are S, F, and SG. So these are the 2 numbers that you will get from the steam tables. Again, note the units that you've got in here, kilojoules per kilogram Kelvin. It's very important to read that information from the top of the column, especially when it comes to conversion of the units, etc. Okay, so the 2 numbers you find are SG and SF. You essentially find these 2 limits on the dry saturated and dry. So I'm looking at these 2 points here. That is SF and that is SG, if you like, on this graph. Something which you need to do then is to find out what is the actual entropy in your case. You know that in the second case, you are at this point, but you don't know where you are along this line. I mean, you know you're at 0.1, but you don't know what the value of entropy for that point is. So what you do, you use the generic equation for X, the dryness fraction, but in this case we use the one related to entropy, and then you find what is your entropy at that point. That is your S at 0.1. In order to find the change in entropy, then what you need to do is just a simple change in the equation. So let's assume that your S1 is somewhere here, because it's 0.1, so it's 10%. So you want to look at this difference here. I'm just going to zoom in a bit here. So I'm interested in this difference in here, S1 and SG. And in order to do that, I'm just going to use a simple way of doing it. So SG minus S, that's what you are after. But just a simple arithmetic really here. You've got an equation for S, and if you do SG minus that, and by factorizing it with respect to SG minus SF, then you find this simplified form. You stick the numbers that you've got for SG and SF, and 1 minus X will be 0.9, and then you find what is the value of delta S. Okay, so moving on to the next example. The third example here is actually quite similar to the first one. It's about a turbine, and you want to find out what is the quality of the steam leaving the turbine. The equation which you would use in this case would be exactly the same equation that we used for the first example, starting with the steady flow energy equation, noting that in this case Q dot is going to be 0, and noting also that the left hand side of the equation will be simplified to m dot H2 minus H1. We've covered that in the previous example, so I'm not going to repeat that again. Essentially, by ignoring the kinetic energy and the potential energy, that term there is simplified to this. And that is potentially the equation that you would use for any turbine you've got. Now, what you need to do, you need to find H1 and H2. And then once you have that information, you already know the mass flow rate. And what you need to find ultimately is the shaft power produced, which is W dot. So looking at the pressure, so the dry saturated steam at a pressure of 10 bar, that is your P1. So you write this down somewhere, and it's dry saturated. So again, note that X is equal to 1 in this example. In fact, it's X1, because that's before the turbine. Then the turbine expands the steam to a pressure of 1 bar. So P2 is 1 bar. Naturally, P2 is less than P1 because this is what turbine does. It reduces the pressure. And that's all the information we have for now. So looking at 10 bar, you either look at page 7 in the superheated steam, or you look at page 4 where you look at the two-phase flow. And then you can find the saturated temperature. The other thing you can find is HF and HG. And again, remember, because X1 is equal to 1, your H will be simply equal to HG. Because that is the equation, that is the sort of the diagram you're looking at. This is the point you are, point 1. If this is a TS diagram, I mean, I normally draw a PV diagram, but in terms of that curve, you would see the same thing in pure substances. So before I do the calculation, I just want to give you what you would expect in this case. So I've got point 1 at a certain temperature, a certain pressure, etc. I know that pressure is going to be higher in point 1. Can you guess what would be the direction of travel, if you like, in terms of moving to point 2? Where would point 2 be in this case? So what we know is that the turbine is an isentropic device. Therefore, you're either going this way or this way. Whichever direction you go, you have to be along a vertical line because entropy is not going to change. The fact that it's a turbine which is the reverse of a compressor, you would expect that the pressure would be reduced and the temperature would be reduced as well. Therefore, you will be going down this line and point 2 would be somewhere here. And this is now why the question is asking you what is the quality of the steam leaving the turbine. It's asking for the value of X in this case, because you're no longer on the dry saturated line. You're going to be somewhere between 0 to 100%. Okay, so Hg and Sg, these are the values corresponding to this point, point 1. The critical thing here is that we know that S2 is going to be equal to S1. So for this point, we already know what S is. And that was what I mentioned as a bridge between point 1 and point 2, which you always have to look for that information which is transferable from one point to another. So moving on to the next page. We now look for the values of pressure, the value of entropy for the second pressure. So the second pressure now is 1 bar. Looking at the steam tables, you find the value of SF and SG. You would need to find SG and SF because these would give you the two limits. So looking at this diagram again, these two values here, what they give you the point corresponding to this point and this point. So you're finding the limits of SS and FG along the same line at that point 2. So simply now, what you can do, you can find out what is the value of X using this equation. Because you've got all the values now, and you can find out what is X, and you find that your steam now is, or it's actually because it's two-phase flow, it's going to be a mixture of steam and water. It's now at 0.872, so it's 87.2% dry. And the last step is to find H2, which you can find from this equation. By finding H2, this allows you to go back to the original equation that we had, and this would give you your power, the power output from the turbine. Any questions? Okay, so these are typical examples that you would expect, you could expect, for example, on this topic. Of course, the first example was much longer, and that could represent the sort of question that you would expect in the exam in terms of the length and the time that you have to spend on that. The other two questions are shorter, and so, but the procedure really is the same. You just look for that information which is transferable from one point to another, and then you try to use a combination of different H equations or S equations or X in order to find the information that is missing. So let's now go back to entropy, the concept of entropy, and talk about and give you actually some equations. Over the next half an hour or 40 minutes, we're going to be deriving and looking at lots of very, very important equations. These are the equations that you would find in your data sheet, most of them. But there are also some equations which are not in your data sheet or formula sheet, but still you need to be able to derive them. So it's very important to pay attention to these. And these are quite fundamental to the concept of entropy. Just a reminder, the equations which are put in a box like this, that just means that they are in your formula sheet. If they're not normally, I try to be consistent, but if they're not in a box, then that just shows that you have to either memorize it or be able to derive it. So starting from the first law of thermodynamics, left-hand side we had the intrinsic internal energy, right-hand side we had the Q and W. Now, we're going to be using some of the information that we've been looking at over the past few sessions. The first thing is a relationship between entropy and Q, and some other information that you've been using in the past. If you remember, whenever you had a moving piston or a cylinder or something where you had a displaced work, you had that equation for work. So if you combine this information now, and if you now, first of all, if you rearrange this and say, okay, so I want to keep delta Q here, and I'm going to move delta W to the left-hand side or to the right-hand side, depending on which way you're looking at. Then I'm going to replace delta W with this. And the other thing which I can do is I can now try to convert or replace delta Q with TdS. Once you do that, you get that important equation. Now, of course, this is in specific properties and parameters. You can have them in the total entropy or internal energy or volume, if you like. Why is this important? This is actually, in fact, this is called the central equation of thermodynamics. As the name suggests, it's actually quite fundamental in thermodynamics. Let's just look at why it is important. It relates pressure to volume, to entropy, and to temperature. So 4 fundamental parameters that you've been looking at in thermodynamics, they're all now related to each other in this equation. So that's why it's actually in this, it's called central equation of thermodynamics. The other thing is that it is actually applicable to both reversible and irreversible cycles. So you don't have to make specific assumptions to say that, well, this equation is not applicable here, or this equation now, cannot be used because of that assumption. No, this equation, that relationship, is applicable to both cases. So irrespective of whether or not the process is reversible. Sometimes this is also known as a thermodynamic identity because of that relationship between all these 4 key parameters. And you can actually derive lots of the equations from this central equation. And you see actually that lots of the equations that we're looking at over the next couple of pages will be based on this. So starting from H, now it's important to use, because I said that entropy has a lot of engineering applications. H is very useful whenever you have some displaced work, and it's probably more useful than just U, because U plus PV would give you the potential of your fluid to do some useful work. So it's important to now somehow bring H into this equation. How do we do that? Looking at H equals U plus PV. Something which you can, of course, do is that you can write in the derivative form, you can write this as dH equals du plus pdv plus vdp, and that represents a dpv. So we're doing it in 2 parts. Now, going back to this equation, if I rearrange this equation now in terms of du equals to tds minus pdv, I've just copied this, just rearranged the equation. Now, by looking at this, I can rearrange this as well, and I can write this as, so du is dH minus pdv minus vdp. So that comes from here. And what you can see is that I can just cancel these 2 terms and derive an equation which relates TdS to dH and VdP. This relatively simple derivation is in fact quite important. If you look at past papers, I mean, we will starting to look at some past papers next year. The difference between the past papers and the tutorials is that normally in the tutorials you just have to start and you have to guess the starting point of the equation. or the question. In the exam papers, what normally happens is that you're going to have part B, sorry, A, B, C, D, etc. And normally in part A, the question is going to ask you to derive some sort of equation, and that equation will be used throughout the question. So if you look at some of the past papers, part A, actually, on a lot of occasions, actually, part A, for example, asks to derive an equation which relates entropy to enthalpy, or something like that, and therefore that analysis which we've just done here would be quite useful to be able to reproduce. So that is another equation which is in your formula sheet, but again, as I said, this derivation is important to remember. Now, what happens if you have a solid or a liquid? So when you have an incompressible fluid or a solid, then things will be slightly different because, as we'll see, actually things are slightly easier. So let's just see how the entropy equation is applied to those situations. And what I mean by solids, for example, remember the example which I gave you last week, which was the a piece of metal, a copper, which was placed in a lake. That was a metal, that was an incompressible object, and you'll see actually now how you would find out, how you would calculate the change of entropy for that situation. So, starting from our central equation of thermodynamics, because this is an incompressible object, thinking about water, or thinking about oil, or thinking about, for example, a solid object, we're not going to have this term, because dV will be equal to 0, it's incompressible. So your equation is simplified to TdS equals du. Also, something else that we know is this. You may not remember this equation, but in fact, if you look at chapter 6, we introduced Cv, for example, defined as du dt. Now, of course, if the volume is constant and the object is incompressible, Cv doesn't make any sense. But still the concept of the specific heat capacity is a physical quantity and therefore is relevant. And therefore that will be simplified to just a C. That's why you see in some equations you don't have Cp or Cv, you only see the quantity C, or a constant C. And that's because Cp and Cv only make sense when you're dealing with gases and compressibility and stuff like that. So that is that equation from there. And therefore, by combining these two equations, you can write an equation for the change of entropy, which is then C times dt over T. If you integrate this now, and assuming that C is a constant, you get an equation which is S2 minus S1 equals C ln T2 T1. And this will be an equation which you will use if you have a situation like that copper in the lake example. That is how you would find the change in entropy. Moving to something slightly more complicated is when we are looking at ideal gases, ideal or perfect gases. So, the first comment, obviously, if you're dealing with vapors and other pure substances in general, of course you're using the steam tables. There's no question about that. That is what exactly we've been doing with the turbine example and ammonia, for example. So that's just very clear. But when you have ideal gases, you're going to use a lot of different equations. And you've seen that before when you had the PV equals MRT equation, the equation of states. You had lots of different derivations and lots of different versions of that equation. And here's going to be the case when it comes to entropy. So you're going to see lots of equations here, but they all sort of make sense, and in terms of simplification and derivation, they are relatively simple. So as you can guess, the starting point is the central equation of thermodynamics. And of course, we have PV equals RT. That was what we know as the equation of state. I just on the previous page, I just explained how we found the definition of CV, which was du dt. Therefore, this allows me to replace du with CV dt, which I've done here. So, if you imagine, I'm now writing this as ds equals du t plus pt dv. So, I've divided the right-hand side of the equation by t. And I want to change and replace du by CV dt. So that's what I've done. That is my du. And the other thing which you can do, you can replace P over T by R over V, because this is P over T gives you R over V. Again, that equation is in your formula sheet. Now, that is a generic equation which relates CV and R to the change of entropy. If you have a perfect gas, and remember there's a difference between a perfect gas and an ideal gas, and the only difference is that the value of CV and CP, actually are constant in a perfect gas, so things are a lot easier. And in that case, because CV will be constant, R is going to be a constant, and you can simply integrate that equation and get S2 minus S1 equals CV ln, that is changed to ln T2 over T1, and that is changed to ln V2 over V1. And you get that equation. And of course, if you now multiply both sides by m mass, you will get the value of the total entropy difference. However, if you want to keep that generic and use it for ideal gases, then because CV is not a constant and it's a function of temperature, you have to keep that inside the integral. So your first term is slightly more complicated. I mean, not complicated, it's just you just have to retain the integral. So if you compare this to this, you see the difference. So this was for CV. So what we've done here was looking at the situations where the volume is constant and you want to express your change of entropy in terms of CV. What you expect is that you can do exactly the same thing for CP. Starting from our equation, the one that we derived on the previous page, and using the equation of states, and noticing, remembering again from chapter 6, that CP was defined as dH over dt. Using the same approach as I mentioned, and doing the replacement very similar to what we've just done for CV, you get an equation for ds, but now this time this is in terms of CP. If you assume that this is a perfect gas, then you can assume that CP is a constant, and then you can solve, or you can do the integration using this. So S2 minus S1 will be CP ln T2 T1 R ln P2 P1. And finally, if you want to keep that generic for ideal gases, then you just have to keep that CP inside the integral. That equation again is in your formula sheet. Now we're going to be looking at a situation using the equations which we derived on the previous page, but looking at a situation where we have an isentropic process. What I would say is that this page is very, very important. Some of the things which we're going to be showing now, in fact, the things which are, the equations which are here, which actually some of you, if you remember, you've seen these equations before in the previous chapters. For example, in chapter 6 again, we used the same equations, we derived some of these equations in the past. But it's very important to understand and be able to find these equations. I can't emphasize enough how important these are. So if you want to put a smiley face or whatever you'd normally put on in your notes and emphasize that this is important to remember the night before the exam, this is, just use that now. So isentropic means ds equals 0. When it comes to the equations that we found for CV, starting with CV now, the left-hand side of the equation will be naturally equal to 0. That was what we found for CV. And in fact, the same equation that we found for CP is the same. So you can now set these two equations equal to each other. And they're both equal to 0. I'm now interested to bring gamma, which is a ratio of CP to CV. I'm interested now to bring gamma into this equation. Now, can you see how we got from here to here, starting from the left-hand side of the equation? Can you see how we got from here to here? Just look at it for a few moments. So we are factorizing it with respect to CV. So R, it suggests that R divided by CV should give you gamma minus 1. Let's just see if that's the case. R divided by CV. So R itself is CP minus CV. And that is CV in the denominator. And because CP over CV is equal to gamma, you get gamma minus 1. So that's how we got gamma minus 1 here. The right-hand side of the equation, very similar. I'm factorizing it with respect to CP. So I should expect that R divided by CP would be this. Can we check that now? So R divided by CP. So you get 1 minus 1 over gamma. And that is equal to gamma minus 1 divided by gamma. These are very simple. These are very simple analysis in terms of just playing with R and gamma, but it allows you to find that important relationship which I mentioned are in here, in the bottom of this page. So make sure you have enough practice in terms of playing with these fractions and quantities and values. Now, if you want to, so assuming that, so looking at the isentropic process, you can start simplifying these equations even further in a way that you get some relationship between T and V and somehow between T and P. So this is what I'm doing now. I want to use that relationship, or the two equations that you've seen here. I want to somehow derive some equations that would relate temperature to the specific volume and temperature to pressure. Because if you have those relationships, then it would be very useful in a lot of situations. So if I integrate these equations here, That's what I'm going to end up with. dt over t would be ln t2 minus t1. Then I've got gamma minus 1. Then dv over v would be v2 over v1. Right hand side, forget about Cp now, because obviously this when you integrate, they will disappear. You're going to have ln t2 over t1 for this. Gamma minus 1 over gamma. And you have ln p2 over p1 for this. Right? So far quite easy. Then, by the way, there's a typo here. This should be T2, and this should be T1. I mean, you'll see that anyway when you do the simplification, but I realized that there's a typo there. So, something to remember is about how we deal with the natural logarithm. I mean, when it comes to ideal gases and perfect gases, as you see, whenever you do integration, because you've got the fraction of dt over t or dv over v, etc., you always end up with ln. So if you're not comfortable with applying some of the rules relevant to natural logarithm here, then make sure you practice on those. And to be honest, the only things which you need here, the only rules that you potentially need would be the power rule, which is ln of, for example, x to the power of y is equal to y times ln x. You must know this anyway, but it's just a reminder. Or, for example, if you've got ln x divided by y, that would be ln x minus ln y. And similarly, ln x times y is ln x plus ln y. I'm writing these three here just in case you want to find how we get from here to here. Now, once you get to that point, then it becomes apparent that t v to the power of gamma minus 1 will be equal to a constant. And in fact, this is not straightforward because you've got t2p1 and here you've got t1p2. But if you do the proper rearrangement of the equations, you get tp to the power of 1 minus gamma over gamma equals a constant. Now, would you be able to do this? Would you be able to move from this point to this point, or do you want me to show step by step? Show? Okay. We may as well, because it's so important. So, starting from the right-hand side of the equation so far. So you're happy so far, right? Okay, so you can see how we move from this point to this point. There's no problem so far. Starting from the left-hand side of the equation, let me just do it on a piece of paper, actually. There are different ways of doing it, but if you've got... So starting from the left-hand side of the equation, and actually, let's just look at the right-hand side, because the left-hand side is quite straightforward. So the right-hand side of the equation, we've got ln of t2 so which way would be best to do it? So, okay, so t2, p2, t1, p1. And now I'm going to write the power here. So minus gamma minus 1 over gamma. And here, again, minus gamma minus 1 over gamma. I've just put the power in red so that you know exactly the difference between that and that. Once you do that, then that is equal to ln of t2, p2, t1, p1, and that would be 1 minus gamma over gamma, 1 minus gamma over gamma. The reason why I've played with the power here is because when you've got that sort of combination, T2 with P1, it's not very straightforward to move from that point to this. But once you do that, then it becomes clear why the power here is 1 minus gamma over gamma. So this is actually, it should be divided by gamma. Okay? So, as I mentioned, by looking at these two relationships, this allows you now, by combining what we have seen in the past, PV to the power of gamma is equal to a constant, you get three different relationships here. 1, 2, 3. The easiest one, of course, is this one, and these two are the byproducts of this through different analyses that you've seen here. I don't suggest that you necessarily memorize these equations, but what I expect is to be able to reproduce them. Yep? Say it again. No. So what I've done, if you imagine, by using that rule here, you've got P2, P1 to the power of minus gamma minus 1 over gamma, right? And I've just started with that, really. If you struggle with that, just come and see me afterwards. I'll explain, yeah? Okay, so the other thing which you might have seen, if you come, I'm just making a note here to refer to page 6.9 and 6.14. Have a look at these two pages in your chapter 6, because on those two pages you've seen similar relationships, so they're all consistent. It's not that you're deriving something else for entropy. In fact, these equations, whether you have an isentropic process or whether you've got, where we had, remember the, let me just show you that on page 6.9, it will be easier to remember. So remember when we introduced the polytropic process, yeah, and we did lots of equations. The relationship that we derived in here, they're actually quite similar. So the analysis which I did during the lecture to get to these equations might be easier, actually. If you want to derive these equations, you can use those as opposed to the ones that I just showed. But in any case, this is the relationship, or these are the three relationships that we see here as well, that you need to be comfortable with. Last point about this is that this could also, you could see this as T to the power of gamma, pressure 1 minus gamma is equal to a constant. So that's an alternative form of TMP. Let's quickly do one example, and then we'll stop there. So, page 8.16, we've got an example to be able to use the relationships that I've been showing you. So, air, initially at 298 Kelvin. As soon as you hear air, you realize that this is not a pure substance. You're not dealing with the steam tables. You're dealing with an ideal or perfect gas, depending on how you want to look at it. And you've got to be looking at the equations that they just derived. So, T1, 298, T2, 505. The process is isochoric, which means dV is equal to a constant. There's no change in the volume. And you want to find the change in entropy of the gas and the heat supplied for a kilogram of gas. These values are normally given to you in the question. So the starting point would be TdS equals du plus pdv. Now you've got the equation of state, you've got the relationship for CV, and then exactly the same approach that we took on the previous pages, you get an equation here. This equation is from the formula sheet, so you can just directly go and jump to this equation. The only thing you realize here is that this term disappears in this example, and therefore you're only left with CV dt over T. Now, when you integrate this, we assume that CV is a constant, so air is taken as a perfect gas. And once you do the integration, you just insert the numbers that we have in the question, and you find your change of entropy in the units of kilojoules per kilogram Kelvin. Again, very important to put the units. If you just put the final answer without any units, you're not going to get the full mark, if that's the exam question. Part B is about the amounts of heat involved in this question. So we want to find out what is the amount of heat supplied to this gas. Because the question says that the process is reversibly heated, and the term reversible implies that you can use this relationship in order to link entropy to Q. If this wasn't reversible, you couldn't use this relationship, for the reasons that I mentioned in detail in the last lecture. So we had the relationship already from here, ds equals cv dt over t. Now we also have this relationship for TdS, and now combining these two equations, I'm combining this, and you end up with this equation here. So a very simple equation for Q12, and it would be the integral of Cv dt. And because Cv is a constant, the integral is simplified to T2 minus T1. And you insert the numbers, and you find the value of heat supplied per kilogram. I mean, the only significance of why the question says for a kilogram of gas, it just simply means that you're after small q, not the capital Q, because small q is per kilogram anyway, and that's the whole point really about that. Question 2, sorry, the second example here on this page is in fact optional. You'll be pleased to hear this. So if you want, if you're free on a weekend and you fancy doing some thermodynamics, just go through this question. It might help. If not, don't worry about it. So we're going to start at this point, and we're going to carry on Thursday. Any questions before we stop? Okay.